This project is a demonstration of the implementation of a convolutional neural network hardware accelerator using an FPGA. This research topic is gaining attention because of the advantages that using an FPGA provides. So the CNN can be implemented on various different types of hardware, including CPUs, GPUs, application-specific integrated circuits, or ASICs, and FPGAs, field programmable gate arrays. But FPGAs are much more suited for parallel computations than CPUs due to their structure. While GPUs are also better suited for these types of applications, they require much more energy, making them a very bad choice for robotics, while the FPGA uses very little energy in comparison. Another advantage of the FPGA is the ability to utilize custom digital logic to perform the many matrix multiplications needed for the CNN. Instead of relying on an ALU to perform the multiplications, we can use simple XOR gates. This advantage can also be utilized in the ASIC implementation. However, the FPGA is configurable while the ASIC is not, which provides a much greater advantage, especially for research and prototyping. Because this topic is very interesting to me, I began looking into the research which is currently being done in this field. I was able to come across the link shown in the first bullet point, which is a GitHub repo containing instructions on how to actually create an accelerator for a YOLOv2 network using the pink Z1 board by Xilinx, which we were using for another research project already. While I did not write all of the code myself, I had plenty of learning experiences in order to get it to actually work. The following bullet points are an outline of the steps needed to create the accelerator. I will go over each one of these points in more detail. So before I created the FPGA accelerator, I wanted to get to see the performance of the network running on a standard CPU. The network that I am using is the YOLOv2 network, which is created from the DarkNet framework. I chose 3 images to do my testing on. So first we'll look at the original image that the inferencing will be done on. Next we'll run the detect algorithm using the weights that we have and that dog image. We can see here all the layers. And here we see our inference results and our time, about 10 seconds. And we can go back and look at the boxed images with the detections. So now that I know the network can correctly detect objects and the performance of it on a standard CPU, I create the hardware accelerator using the Vivado tools. Using Vivado HLS, C++ code was synthesized into Verilog, which describes the data paths and matrix multiplication units which will be generated on the FPGA. The IP, which was created in Vivado HLS, was then used along with the Zinc 7.0 processing system and some AXI buses to generate a final bit stream. The image on the left is the block diagram mentioned earlier. The 2 images to the right show some estimated utilization and power consumption generated by Vivado. Here we can see the pink Z1 board as well as the Jupyter Notebook interface used to run the inferencing. So the pink Z1 board is a combination of programmable logic and a CPU. The CPU boots from an SD card containing the pink system image. The pink system uses Jupyter Notebooks to run Python code, which loads the bit stream, loads the input image, and handles the task of running the forward pass through the network. So here we'll open up our Jupyter Notebook. We'll go to the file containing the inference algorithm. Here we see we're going to use our dog.jpg, which is stored using the internal memory of the FPGA board. Now we'll run all the cells. And most of the time is taken by the actual setup of the logic itself. We can see here that the FPGA process time was around a second, everything else under a second. This is a lot faster than the CPU implementation, which took around 8 seconds. You can see we still have a correct inference. As we scroll back up through the code, you can get a little bit of an idea of how the size of it. And that's about it.